So welcome to the tutorial session 9 for the course problem solving through programming in C. So there is a SWAYAM course that has been floated by Professor Anupam Basu from Department of CSE IIT Kharagpur, and I'm Siddhant. I'm one of the 3 TAs who are in charge of taking these tutorial classes, where we'll be covering the week's concepts and solving a few questions which will help you out with the assignments as well as the final exam. So for the week 10 we looked at bubble sort, and we also had a brief idea of how pointers work in case of arrays, and how to do call by references and so on. Alright, so keeping that in mind, so let us start with the first question, which is regarding bubble sorting. So I'll just briefly give an example of how bubble sorting works. So let us say that we have an array which is like 4, 2, 8, 1, 7, and we want to arrange it in ascending order. Now we want to arrange this array in ascending order. So what basically we do is we go through the entire array and we swap the and we compare and swap all consecutive elements, and such that the highest element moves to the bottom. So here first we compare 4 and 2. We find out that 2 is lesser than 4, so we change their order, so we swap them. So the first swap gives us this. Then we check, so we check this and swap. Then we check this, which is fine, so no swapping here. Then we check this, 8 and 1, then we swap. So this is the next after swapping, this is what we get. Then we check 8 and 7 and we swap that. So we get, after the first pass across the array, we get this as the output. So you see the last element is sorted in the order. Now we only have to check across this remaining elements, all elements but the last. So now again we start comparing and swapping the elements based on whichever is high. So we compare 2 and 4, but no swapping required. Then we compare 4 and 1 and we swap them, so we get something like this. Now we compare 4 and 7, but no swapping is required, right? So this is the end of the second pass, and you can see that both this 7 and 8 are now sorted. So we'll look at only the remaining elements, that is 2, 1 and 4. Now what we do is we check the first 2 elements, we check this 2, and then we swap based on that. We swap that and we get this, right? Then we check 2 and 4, and as you can see, no need of swapping, and then we get this 3 are sorted now. Now we have this is the third pass. Now after in what happens in the next pass, we compare this 1 and 2 and we find out no sorting is required, so the array is now sorted. So we get this as the final array. So as you can see, if we have to arrange in ascending order, we keep on comparing and swapping the elements such that the heaviest element, that is the highest value, goes to the bottom of the array, and so on. So finally we get this array. Now you can see that we already had obtained a sorted array at this point. We didn't need to check this 1 and 2, right? So if we had some boolean values swapped, which became and we could find out from the value of that boolean that no more swapping is required, we could have just stopped midway, right? That would have increased the time efficiency of the bubble sort. So that is what this case asks you, that how can you improve the best case efficiency of the bubble sorting algorithm. Assume that the input is already sorted. That is how you consider the best case sorting. So let us see. In the best case sorting, what happens, instead of this we have basically this. So the array is already sorted in a certain manner, and say it is sorted in this in ascending, and you have to sort the array in ascending. So which of these cases, which of these options will exit the bubble sort in the minimum amount of loops or minimum amount of comparisons and swappings? So let us check that out. So we have a boolean called swap in all these options, and we are setting the value initially to true or false, and then in the for loop itself, in the conditional checking for the for loop, we include this swapped should be true. So both these conditions should be satisfied because this is a logical AND. So we need both these conditions to be true, which is j is greater than equal to 0, as well as swapped should be true in order for the loop to continue, for the bubble sort to continue. So what this does is, if sometime we find that there is no swapping that is taking place, the loop will simply exit. So here what we do, so here we go we check 1 and 2, no swapping required. Then we check 2 and 4, again no swapping required. Then we check 4 and 7, no swapping required. 7 and 8, no swapping required. So at this point, this is the first pass, and there is no swappings involved. If no swapping is involved, then if we set this swapped to false, in that case the swapped here in the conditional for the loop will just make the thing exit the loop, because this a logical AND will give a true output only when both the inputs are true. So the swapped, if it becomes false, then it will simply break the loop, right? And we as you can see, we don't really require. So if you have a already sorted array, you can just go in a single pass, you can say, and once there is no more swapping in that particular pass, you can just simply say that the array is sorted already, because there is no swapping that is taking place in the previous pass. So it's already sorted. We don't need to continue the bubble sort any longer. It is just inefficient. Okay. So what do you think should be the answer here? So keep in mind that we are setting the swap to false. So I'll just tell you this, that answer is between B and C. So we set the swap to true initially, because in the for loop the conditional is checked initially after the initialization step, which is j equal to arr.length minus 1. You will have the conditional being checked. So once the conditional to get through that conditional, we initially set the value of this boolean variable swapped to be true, and once the conditional is true, we set it to false, and then we do all this swapping. So this entire part is actually the swapping of the two variables, which is k and k plus 1, that is the location k and k plus 1. So we do this swapping here, and if there is some swapping that has taken place, then we set the value of swap to be true. So you can see that initially we had this swapped value to be false, and now we went through this entire we went through all the elements of the array, and we compared them, and we found out that there is some swapping that is occurring. So we simply set the swap value to true, so that if there is even a single swapping that has taken place in that particular pass, this bubble sort will still continue to run. Once in case there is, for example, in this example, if you consider this one, then in this case you will never get an element where ARR of k is greater than ARR of k plus 1, because it is already sorted in ascending order. So you won't find any cases where the ARR of k plus 1 will be greater than ARR of k. So this if condition will never be satisfied, and this the if part will never run. So the swapped value will never be true in that case, and once it is not true, when we go outside the k loop, and the conditional checking again occurs for the j for the j loop, you find that the condition swapped is false, so the loop just breaks. So if you use this particular algorithm, which is optimized for bubbles, it's an optimized bubble sort, so you can actually do this operation in a O of n efficiency, that is time complexity. So this has a O of n time complexity, whereas for the best case, of course, for the best case, this optimized bubble sort has a order of n time complexity, because you are doing only n operations. Why n operations? Because you are comparing, say you have 5 elements here and you are comparing it four times. So 4 comparisons you are doing. That means you are doing n minus 1, you are doing n minus 1 comparisons, or rather n minus 1 operations. So this is order of n. So that is why we have order of n time complexity for the optimized bubble sort. However, for if you didn't have this swapped conditions and so on, the time complexity would have been O of n square, even for the best case. So you are saving a lot of operations here. Is that clear? Okay, I can what I can do is I can just go through right. So for this particular algorithm, for the part C, what I can do is I can go through one particular condition. So say j is equal to ARR of length minus 1. So here ARR of length will give you 5 minus 1, which is 4 basically. So we are setting j is equal to 4, and j is equal to is greater than equal to 0, and swapped is true currently, right? And this is true. So this condition is satisfied. So what happens in the k loop? K goes from 0 to k less than j, so it will go up till 3. So when k is equal to 0, that means you are checking ARR of 0 greater than ARR of 1, right? So ARR of 0 is 1 and you are checking it against 2, so this is false. So this entire thing will not work. So now what about k1? So when k is equal to 1, we have ARR of 1 compared to ARR of 2, still false. And similarly ARR of 2 compared to ARR of 3. So ARR of 2 means 4 compared to ARR of 3, which is 7, still false. Now similarly ARR of 3 compared to ARR of 4, where we are comparing 7 and 8, so still false. So this swapped will never become true, because this condition is never satisfied here, as you can see. So if swapped never becomes true, the next time we come to j is equal to 3, so when we reach j is equal to 3, because there is j minus minus, right? So we reach j is equal to 3, from j is equal to 4 we reach j is equal to 3. In that case, when it checks for the condition j is yes, j is greater than equal to 0, but is swapped true? No, swapped is not true anymore, swapped is false. This part is, so this part is false, because we set swap to false, right? And it never became true later on. So this part becomes false and the loop will exit. So the so we did how many comparisons? We did only 4 comparisons and no swapping. So total of 4 comparisons. That means for an array of size n, we did n minus 1 comparisons, which means order of n. So we are optimizing the bubble sort, at least best case efficiency for bubble sort by using this. Okay. All right. So I'll just move on to the next question. So this has so in this question, it's basically about the call by reference and the difference between call by reference and call by value. So as you can see, we have a function called func, which is of type void, very important. It's of type void, and it takes an integer input, that is x, and it sets the value of x to 40. Now in the main function, what we do is we initialize a variable which is y. We set the value of y to 30, and we pass the y to the function called func, and then we print the y. So what should be the output here? So it's fairly straightforward. So what happens here is a call by value, right? So what happens is here is a call by value. So what happens is we are sending the value of y to this function. So basically we are kind of calling this function of 30, okay, and so when it reaches here, x is 30, but inside the function we make x equal to 40. So what happens after that? So once x equal to 40, nothing happens because it's a void function. It is not supposed to return anything. So even if x has changed its value to 40, it is not the actual variable. X is not the actual variable that we had. It's a formal parameter that so this is called the formal parameter, and this is called the actual parameter. So y and x are not the same, just the value has been passed, so not the location. So even if we change the value of this x, it will not affect the value of y. So when we print y, we will still get a value of 30 here. Now this is the call by value. But what would have happened if say instead of this we would have used this, right? So what would have happened if we had done this? So here what I am doing is I am sending the location of y. Similarly, instead of int x, it would be written int star x, and here it would be star x equal to 40. Okay, so with this many changes, so what would have happened here? So here I would pass not the value but the reference. So this is a call by reference. Reference meaning the reference of the location of the variable. So when I write this ampersand y, that means it sends the location of this variable to the function that is called func, and then because this star x, this pointer x, still points to the same memory location that that y is pointed. So in the RAM, say this is the RAM, we had some memory location, and we had the value of y was being stored here. So y, it had a value of 30, right? So let me just redraw that. So we had y where we are storing 30. Now what I did is ampersand y, which is the position of this y, I sent it, and it is being stored in x, because that is what I have done. I have called this I have done a call by reference. So I send the position of this variable to the function called func. Now this x, which is a pointer, will store the location of this variable. So x now points to this particular location. So now it points to this particular location. So when I write star x equal to 40, so whatever value is being stored at this pointer location will be changed to 40. That means now instead of 30, you will have the value of 40 being stored here. Even if it's a void function, doesn't matter if it's a void function, the value stored here will become 40, because x is pointing to the location of y, and we are saying that whatever value there should be at the location that x is pointing to should be 40. That's what the star x equal to 40 means, right? So when we return to our main function and we try to print y, now the variable space, the variable, or rather the memory location where y is being stored, the value has already changed to 40 in the function func. So now if we try to print it, you will get 40 as the output, not 30. So this basically tells you how call by value and call by reference differs. In call by value we just send the value of the function, and in call by reference we send the memory location of the function, or rather a pointer to the function, a pointer to the variable. So that is how it is different. So is that clear? All right. So in this week's lectures we also learned a bit about bisection method to find the root of any function. So I'll just briefly tell what bisection method does. So say you have a initial range which is 1 and 5, and you have a function. So here the function, say f of t is equal to t e to the power minus t minus 0.3. So this is your function, and you want to find the root of this function, that is, where does this, for what value of t does this f of t go to 0. So f of t goes to 0 at what t. So that is what you need to find, the roots of the function, right? Now how do you do it? You have to take two initial assumptions, which are it should be taken in a very proper way, in the manner that, and here it has already been told to you that take the initial range to be 1 to 5. So what we will do is we will calculate the value of f of 1, and we will calculate the value of f of 5. So here you should notice, okay, I'll just do the calculation and we'll see what we get. So we get f of 1 as some 0.07 or 0.67, whatever, and f of 5 as so you get minus 0.266. okay, so basically you can see how the initial conditions have been taken. So in bisection method it is very much required that your initial conditions, the two initial conditions that you take, should have opposite signs in the function. So basically, if say you have a function like this, and you need to take an initial condition 1 which is on this side, say here it is 1, and 1 on this side. So here you can see that one value is positive and the other value is negative, right? So you need to always have two initial conditions which are on opposite sides of 0. So this is the x and y axis, or rather here t and f of t, right? And you need to find out this particular point, this where the function is going to 0. But here the question is asking what is the second iterative value of the root. So we'll just do two iterations. So this let's do the first iteration. The first iteration, we see that 1 and 5 are on opposite sides of the root. So we calculate the value at this. We check the middle point of this. So this is basically 3, right? So we calculate f of 3. Now if you calculate f of 3, you will get s3 minus 0.3. So you will get some minus 0.151, right? So if you get minus 0.151, that means it is somewhere around here. It is closer to the root than 5, but it's still not there. So now what we will do is we will take 1 and 3, because we will take the closer one, which is 3 instead of 5, and the one on the positive side, which is 1. So what we will do, again the same thing, we will add, we will take the midpoint of 1 and 3, and that is what? That is 2, right? So we need to calculate f of 2. So if you have f of 2 minus 0.3, so it's roughly minus 0.03. okay, so it will be somewhere around here. will be 2, right? But and this is the second iteration. So this was the first iteration, and this is the second iteration of the bisection method. So after the second iteration, the root that we have found is 2. So here, that is what actually is being asked. What is the second iterative value of the root of this function? So we got the answer to be 2, right? Because that is the iterative root that has been found after the second iteration. But you can still continue this, taking f of 1 and f of 2, because 1 is still the positive value, 2 is the negative value. So you can still take it at 1.5, which is the midpoint of 1 and 2, and then you can still calculate this until you reach very close to 0. So whenever you reach very close to 0, whatever value you have, whatever t value you get is the root of this particular function. So this is how the bisection method works. I hope it's clear. Alright, so let's move on to the next question. So here it's a quite straightforward question on pointers. So we are defining a pointer. You can say star ptr, and we have a integer variable which is a equal to 12. It has been initialized to 12, and what we are doing is we are in this statement we are saying that this pointer ptr, it points to, so ptr now points to the location of a. Okay, so this is what we basically say, that the ptr, the pointer which is called ptr, points to the location of the variable a. So now ptr is a memory location, so this is a memory location which holds the value of a, that is 12, right? Now then you do this particular step, which is basically whatever value there is in star ptr, we are so basically what we are doing here is star ptr, which is 12, minus 2 into star ptr, which is 12. So we get minus 12 here, right? Now you see we get star ptr is minus 12. That means whatever the memory location of a was, so a, this was the memory location of a, and ptr was a pointer which was pointing here, and we changed the value of the memory location that ptr was pointing to minus 12. So if we are changing the value to minus 12, so that is what will be stored here, and the value of a, if you find the value of a, it will also be minus 12. Why? Because you have both the things point to the same memory location. So the variable a and the pointer variable ptr are actually referring to the same memory location. So if you change the value which is associated with the pointer ptr, it will also that means you are also changing the value of the variable a. So when you print this, you will get minus 12 comma minus 12 as the output. Okay, I hope it's clear why the answer is minus 12 comma minus 12. So the same logic as the previous call by reference example that I explained, the variable a and the pointer variable ptr both are actually referring to the same memory location. So if you change the value of whatever is being stored in the memory location ptr, it's the same as saying that I'm changing the value of a. So here you get minus 12 comma minus 12 as the output. Now for the next question you have to work it out yourself. I'm just going to do probably the first 1 or 2 steps. So it's again regarding the bisection method. The answer is up to 4 decimal places. So this can be a possible numeric answer question. So keep that in mind. So we have to consider only the root lying in the positive quadrant and compute the root till 5 iterations only. So all these details have been given to us, and we have the function as well, which is x into e to the power 2x minus 3x square minus 5. So what we do is, we know that we need to find the value in the positive quadrant. So let's first check the value at 0. So it is minus 5, as you can see. Next we check the value at 1. So let me compute that. So we have it is about 2 minus 3 to 1 minus 5, so it gives minus 0.611, right? So it's negative, it's still negative. So we need to check the value at f of 2. So what will be the value at f of 2? We have this 4 into 4 minus 5, so we have a value of 92.196. So now as you can see, this 2 can be our initial conditions, right? So 0 and 2. So the next thing we do is we calculate, in the first iteration we do this, which is basically 1. So f of 1, as we know, it's negative, or actually, you know what, let's not take this as the initial condition, it's foolish. Let us take this 2 as the initial conditions, because this is the nearer value that we have seen. This is minus 5, which is much farther than the root, and this is the nearer value. So let us take 1 and 2. So in the first iteration, when we do the first iteration, we will calculate f at 1.5. So if we do that, we will have a to the power 3 minus 3 into 1.5 square minus 5. So we have some 18.38 as the value. Now this is a positive value, as you can see. So for the second iteration, what we will do, we will check 1 and 1.5. so our mid value will be 1.25, right? And we will again calculate for 1.25. So we get a value of 5.54. Now again positive. So next, for the next one, we'll take 1 and 1.25 as the for the third iteration, we'll take 1 and 1.25 as our range, and again we will calculate and we'll get 1.125, and we'll continue. So we'll continue this till 5 iterations, as has been asked here. I think you will get a value of 0.0132 or something of this sort. I think it is close to this, roughly like this. You can check that. You can continue doing the iterations and find out the answer. All right, or maybe not 0.132, but 0.125 or something. Anyway, I'll calculate it and I'll write it down when I upload this PDF. All right, if this is pretty much the same bisection method, just that we have to do it for 5 iterations. And yeah, so let us move on to the next question if there are no doubts here. All right, so again we come back to bubble sorting. So here, as you can see, this is the array that I was using earlier. So you have an array of 7, 4, 1, 8, 2. So this is your initial array, and what would be the correct bubble sorting steps to sort it to ascending order? So yeah, it has not been written, but as you can see, the options are in that way that you are setting it to ascending order, right? So what should be the correct answer here? So first, what do we do in bubble sorting? We go in the first, so in the first pass, what will happen? We compare 7 and 4, and we see that 4 is less than 7, so we switch 4, 7, 1, 8, 2. So that is our first swapping. Then we compare 7 and 1, we swap. So you have 4, 1, 7, 8, 2. Then we compare this 2, no swapping required, right? So next we compare this 2, no swapping required. Then we compare then we compare this two and we swap. So 4 1 7 2 8, right? So this is our first pass. The first pass is complete. We have gone through the array once, and the last element is already sorted, so we check in the remaining. Now what happens in the second pass? The second pass, we already have this, so what we do is we start checking 4 and 1, we switch, so we have 1 4 7 2 8, right? Then we check 4 and 7, nothing required. Then we check 7 and 2 and we switch, right? So 1 4 2 7 8, and that's all. So this is in the second pass. We already know that the last two elements are sorted, so we just need to look at this. Now we'll look at the third pass. Now in the third pass, what we do, we check 1 and 4, nothing required. 4 and 2, we switch because 2 is less than 4, so we do that and we get this. And here we know that this is the last three are sorted. Now in what happens in the fourth pass, we check. So we check among this two, we check this, no pass required, so we have our sorted array, which is this. So you can see which of these options are matching with this. So in our first step was 4 7 1 8 2, then you have 4 1 7 8 2, I think. Yeah, this is the correct answer. Option B is the correct answer. Is that clear how this bubble sorting is happening? Alright, so let us move on to the next question. So which of the following statements is correct for the two arrays with respect to A and B? So we have the first statement that we have is star x of 5, and the second statement we have is star in parenthesis y of 5. Now which of this is an array of pointers and which of this is a pointer to an array? That is what we need to know. So it's basically an array of pointers would be an array where each value is pointing somewhere. So so this is basically each element is a pointer and it points somewhere. And pointer to an array basically means that, yeah, I mean it's pretty clear. It is a pointer which points to an array, points to in this case the first element of an array. Right, this is the difference between these two things. So in so if you try and try this out on a IDE, you will find that both of this x and y that have been defined here are actually array of pointers. So here option B is the correct answer. So in both these cases you have defined a array of pointers, which is a case where each element of the array is a pointer somewhere, right? And this actually introduces a word called dangling pointer. So this is basically a pointer which points nowhere. So why I am saying that is because when you define this this array of pointers, it basically consists of say 5 pointers, but you are not specifying those pointers where they should point to. So you are not specifying where they are supposed to point. So when you just define the pointers like this, an array of pointers like this, it points nowhere, and such a pointer which points nowhere is called a dangling pointer. Okay, and it can be potentially dangerous. So when you define a pointer, make sure that it points somewhere, or do not use it before having it point somewhere, right? Okay. Now if this way, if we initialize it in, if writing the declaration in this way defines an array of pointers, how exactly do we define a pointer to an array while mentioning the array size? So let's check that out. We'll see it in the last slide that I have, but before that we can solve two more questions related to the pointers. So let us see the first question. We have a int main which is taking a void input, which is no input, and which has a, we have an array a which is basically 10, 12, 6, 7 and 0. So I'll just write the index here because for this question it will be important. So the index is as follows. So you have from 0 to 4 and you have a pointer p which points to which is basically a plus 4. So when you say a basically points to the first element of the array. So if you remember the way that arrays are defined in C, so if you define a array variable a which is initialized to this particular, these all values, so a actually is a pointer which points to the first element of the array. So it points to the value, the memory location containing the value of 10. Now when you write p is equal to a plus 4, so you just that means an array are contiguous memory locations, so you go 4 away from a. So this is a plus 0, this is a plus 1 plus 2 plus 3 plus 4. So p actually points to this, the last element of the array. So when you write p is equal to a plus 4, so it basically does, this is a plus 0, this is a plus 1, this is a plus 2, this is a plus 3 and this is a plus 4, because they are contiguous memory locations, so you can access them by this. So this statement is the same as saying this. So p is equal to ampersand a of 4. I mean it's the same, both of the statements are the same. So p is a pointer which points to the memory location of a of 4, which is having this value of 2. Now what I do is I have a for loop from I0 till 4 and I print p of minus 1. So what does p of minus 1 mean? So let us see the iterations. So when I is equal to 0, we are printing p of minus 0. That basically is, so what this p of 0 means is star p minus 0. Alright, so that means star of p. Star of p is what? Star of p is 2. Now when I is equal to 1, we are saying p of minus 1, which is same as saying star of p minus 1. That means p, the one before the element or the memory location just before p, that means this particular memory location. So this is, if this is p, then this is p minus 1, p minus 2, p minus 3 and so on. Okay, now so p minus 1, the value is 7. Then you have I is equal to 2, p of minus 2, so star p minus 2, value of 6. I equal to 3, p of minus 3, it is star p minus 3, value of 12, right? I is equal to 4, p of minus 4, that means star of p minus 4, that is value of 10. So as you can see, for each of the iterations, when we print p of minus I, so it prints this in this order. So we have 2, 7, 6, 12, 10. So option D is the correct answer. Is that clear? So if I just rewrite that, it will be something like this: 10, 12, 6, 7 and 2. So this is a plus 0, this is a plus 1, this is a plus 2, this is a plus 3, this is a plus 4. Now if I write it from p, so this is p, this is p minus 1, p minus 2, p minus 3, p minus 4. Why? Because p is equal to a plus 4. So you can see how it is similar, right? So the location, so p minus 4 is the same as a, and p is the same as a plus 4. So this is how the array is, the memory locations a and p are related. Okay. Alright, so let's look at the next question. It's quite straightforward as well. So we have a variable a which has been initialized to the value of 5, and we have a pointer ptr which points to the variable a. Now is the same thing again. If we have a variable a with some value 5, and now we are saying that this ptr, it now points to this particular variable or this particular memory location. Now we say that this star ptr is equal to star ptr minus 3. That means whatever value is in this memory location, we deduct 3 from it. So if we deduct 3 from it, then what happens? So you have, okay, you have 2 now. So you deducted 3 from it, and you had 5, you deducted 3, you got 2. So now if you print 2, if you print star ptr and a, both of them will give you 2 comma 2. This will be your output. It is quite similar to the one that we just solved in I think 2 slides before. So yeah, so you will get 2 comma 2 as the output here. Okay. If you have any doubts, you can just unmute and ask, or you can write in the chat box, and I'll answer it accordingly. Alright, then we can look at the next question. So this question basically tells us about the worst case complexity of bubble sort. In both the questions basically ask the same thing. So the first question here, which is this, asks that what are the maximum number of comparisons can occur when a bubble sort is implemented. So a maximum number of comparisons will happen when you are calculating the worst case complexity. That means the array is completely unsorted, or rather it is sorted in the exactly opposite manner that you want, that you don't want. Say you want an array in ascending order, you want to sort in ascending order, and your array is in this 8 7 4 2 1. This is your array and you want to sort it in ascending order. So this is your worst case complexity, and this is where you will have maximum number of comparisons and swapping operations, right? So that is what has been asked for in the second question as well, which is the worst case complexity for bubble sort. So I'll just take that array and I will calculate it. So I'll take this as an example. So what happens in the first pass? Let's see what happens in the first pass. We compare 8 and 7, we switch. So now we have this. We compare 8 and 4, we switch, we have this. Then we compare 8 and 2, we switch, so we have this. We compare 8 and 1, we switch, so we have this. So this is the first pass. We did 4 comparisons and 4 swappings, right? What happens in the second pass? So in the second pass we have this. 8 is already sorted, so we need to check among this, right? We start comparing this, we exchange the values. So we have 4 7 2 1 8. Next we compare 7 and 2, we exchange, so you have something like this. Next we compare 7 and 1, we swap, so you have this. So these two are sorted. So you have basically this is also counted here. So 3 comparisons, 3 swappings, or maybe I can just rewrite that for the sake of to keep it legible. So 74218, and we swapped 7 and 4, right? So 3 comparisons and 3 swappings. That's what happened in the second pass. What happens in the third pass? In the third pass, we have this array which is 4, 2, 1, 7, 8, out of which 7 and 8 are already sorted. So here 8 was already sorted. Now we need to check only in this. Now the first thing we check is 4 and 2. We exchange it. 2, 4, 1, 7, 8, right? Now we check 4 and 1. We exchange. So 2, 1, 4, 7, 8. And we know that the last 3 are sorted now. So this is the third pass. So we did 2 comparisons and 2 swappings, right? Now we go to the fourth pass. In the fourth pass, we have this array, out of which this much is already sorted. We compare in this. So we compare, we exchange. So we get 1, 2, 4, 7, 8, and everything is sorted. So this is where we stop. So what did we do? We did 1 comparison and 1 swap. Now if you calculate the total number of operations, we had 4 plus 3 plus 2 plus 1 comparisons plus 4 plus 3 plus 2 plus 1 swappings, right? So if you for a array of n elements, if there are n elements, basically you have n into n minus 1 by 2 into 2. So basically n into n minus 1, that means order of n, n square, right? So that is basically what is being asked. So how many number of comparisons out of this? It will be n into n minus 1 by 2 comparisons, and you will have n into the same n into n minus 1 by 2 swaps, right? And overall the time complexity will be order of n square. So the worst case time complexity is order of n square. Is this clear? So you can try this exam with any example by taking any of the examples. So the best case complexity, as we saw, was order of n. The worst case complexity is order of n square. So the average case complexity, what is the average case complexity? So anything between the best and the worst. So you will have the average case complexity of order of n square. Okay. Alright, so now we look at the thing that I told you earlier. How do we define a array and a pointer to an array? How do we do that? So earlier we had seen, just to remind you, we had checked this of 7, right? And in bracket y of 7. So I have just changed it to fit this. So we have defined this to int. Alright. Now here let me tell you that size of a pointer variable is 8 bytes for 64-bit machines and 4 bytes for 32-bit machines, no matter what kind of pointer it is. Alright. And here the size of float is 4 bytes for 64-bit machines. Okay. Now in this question, what has been asked, if we define a float star x, a 2D array 7 cross 2, so what is the size of star of x? So that is what has been asked. So for this we need to know whether x is a pointer or x is an array. So what exactly have we defined here? That's what we need to know. So here, as it turns out, if we write it in this manner, star of x in then 7 cross 2, you are defining a pointer x. So here what I am doing is I am defining a pointer x to an array, or to, rather, let me write to a float array of 7 cross 2. So this is what you are doing here. So you're defining a pointer x to a floating point array of 7 cross 2. So when you do a size of star x, so a size of star x will give you 7 into 2 into 4, which is 56 bytes. 56 bytes of space is being consumed by this star of x. So this is this. Now what if you write size of x here? So size of x, what will size of x give you? So x is actually a pointer. Star of x is the array, but x is the pointer. So if you write size of x, you will get simply 8 bytes. So that is what you will get. So similarly, what if we write size of x here, in this case, or rather let me write y, size of y, you will get 56. So 7 into 8, which is 56, right? One pointer, it's array of pointers. One pointer is 8 bytes, so you get 7 into 8, which is 56. So I hope you are able to distinguish how to define the pointers, array of pointers, and a pointer to an array. So this is a pointer to an array, which is 7 cross 2. Okay, if that is clear, then I'll just discuss the last question for the day, which is how would you write a pointer expression for accessing ARR of 1, 1 of 5 of 3. So this is a 3-dimensional array, and we are indexing the indexes that you want to see is the second element in the dimension 1, sixth element dimension 2, fourth element dimension 3. So let us deconstruct it from the from the first dimension. So ARR simply points the first element of the first ARR. If we write just ARR, that is the memory location of the first element of the entire array. So in all the dimensions 0, 0, 0. So ARR of 0, 0, 0. This we can simply write as star of ARR. Okay. Now if we write ARR of 1, 0, 0, what do we write? Okay, not exactly this. I'll tell you why not. This has to be written as star 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 ARR. Why? Let me rewrite that for you. Why? So this is ARR of, so ARR plus 0 star. That means it is you are now in the first dimension, 0th first dimension, first element. Then again second dimension, first element. Third dimension, first element, right? So as you can see, so in the same manner, so if you just remove all these brackets because it's 0, you get this star 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 ARR. So similarly, now if I have to write ARR of 1 of 5 of 3, then what we can write is ARR plus 1 star. So we are pointing to the, in the first dimension, the second element or second row or column or whatever. So we are pointing to that. Then plus 5, again another star. That means the second element or the second row in the first dimension, the sixth row in the second dimension, you'll still have a few elements, right? Now next plus 3, another star. Now in the third dimension you are looking for the fourth element and the value of the fourth element. So this is the value that you want. If you remove this last star, you will get the memory location of that particular element. Which element? The second row, sixth column, and fourth, in the third dimension, the fourth element of that particular row and column. Okay, so so here the correct answer is option C. Okay, is that clear? So if that is clear, if you have any doubts, you can ask it in the chat, or we can end the session here. All right, then let us end the session here. So I hope you could understand the concepts, and if not, then you can just ask me in the next class. So the next class will be on the next Tuesday, 7 to 9 p.m. So thank you for joining.